My name is Jirka Hlinka. I am from Prague, Czech Academy of Sciences, Institute of Physics. But no matter where I'm from, I'm very happy to be here. It's just a wonderful place, and we have just wonderful time together. And so I think the first thing I would like to ask you, if you agree with me, to make big applause to the organizers and Vincent in there. Okay, this was my first exercise for you. I am going to talk about macroscopic symmetry breaking. The subject is a little bit multi-meaning. I mean, the title you can understand in a different ways, and I will also explore it in different ways. It somehow relates a lot what has been already said in this school by Mael, Martin, Michel, Morgan, and Maria. So all what remains me to make a test whether you listened well. And no, don't worry. I'm going to explain everything, and I'm trying to explain in a way that I hope all of you who listened will understand. So there is this macroscopic, which means here basically point group, breaking of point group symmetry, and most of the talk will be about crystallographic point groups. There are 32, and Mael has introduced them very well. And let's say the main goal of my talk would be to, let's say, invite you in using a tool which allows a little bit to explore symmetry breaking of point groups. And I'd like to convince you that it's easy on the one hand and useful on the other hand. There is also this concept of symmetry breaking. Maybe this needs a little bit of clarification because it has two meanings, this breaking. So there could be a breaking of symmetry by external force or external influence, or the system itself can spontaneously break the symmetry. So I probably have seen this, but I will do some simple demonstration. So this stick is supposed to be straight. And if I put some force in direction, for example, to your left, well, anyway, it bends in this direction. I can do it in the other way around as well. It bends. But also, if I try to elongate it, I don't break the direction, it stays straight. But sometimes if I exaggerate it, it also breaks the direction. But this is the spontaneous one. So spontaneous one, some people say, is breaking the Curie principle. I was reading the Curie paper. Maybe some of you who read it in French original would say that it's not so obvious what is meant in that paper. So I let you to think about it's really against the Curie principles, because he's talking about cause, and it's not very clear to me what he means by cause, because of course the fact that finally the spontaneous breaks in some way, it's perhaps related to some small cause, which we don't see, but anyway, that's a sort of philosophic thing for late night in the beach or something like that discussion. So mostly I will be talking about spontaneous symmetry breaking, where the cause is, for example, temperature, which doesn't change the symmetry by itself. The cause doesn't change anything from the point of view point group symmetry. And this is what is the main goal of this talk. The phase transitions often happens due to even if you have hydrostatic pressure or some scalar influence on the system. But of course, these things can be also used for the symmetry reductions, which are induced by something which is lowering the symmetry. So that was about the breaking. Actually, before going next, I'd like you to focus on one point. And I need to make a point. So let's see. I make it a little bit bigger so that you can see it. So I like you to make exercise for 2 seconds, concentrate on the point, and try to forget everything around you. It's important that you did this exercise, because now, if you forgot about everything around and you are a physicist, then you somehow have mental understanding what is the point group. Point group is the symmetry of the point which is in space like that and doesn't move from our reference. So what does it mean? What is actually the symmetry? So I'm considering the symmetry in space and time, sometimes in time. And so this, so anyone knows the group of symmetry which leaves this point, the maximal group we can imagine? So identity is leaving the point, but there are many other elements which are leaving the point, symmetry elements. So for example, we can imagine an axis. We can rotate by axis which Mael calls 2 or 3 or 4, but because there is no lattice, we can do also 7 or 5 or 2017. And so in principle, we can do infinitely small rotations. So the axis is of order of infinity. So in international notations, analogical to which was introduced by Mael, Mael likes the group M2, right? So it's like instead of 2, we put infinity. But you can have also so this is this axis, right? But you can have also perpendicular axis, and you can also rotate. So to describe, to keep this in mind, we put in the symbol 2 axis, one principal, one which is perpendicular to it. Of course, they are equivalent in energy. Is it all symmetry operations? Huh? Inversion. Yeah, inversion. But if you combine inversion with twofold axis mirror, so we usually prefer to write mirrors in these symbols. So this would be the symbol which describes all symmetry elements of that point. And from the group, from those who, I can write a different symbol for the symmetry. Anyway, so there are no translations. They're just all possible rotations, proper and improper. Now, please close your eyes for 3 seconds. Everybody, close your eyes. Don't cheat. Now, open your eyes. What do you see? 2 points, right. There are 2 points. We have more information than before. We have 2 points, so we have made the symmetry lower. We have broken the symmetry already. Yeah? We have 2 points, so now we know that there is a direction, or there is an axis which goes through the points, and there are other axes which are not going through the points, and they are not symmetry elements. Yeah? So the number of symmetry elements has decreased. And so, and if you were not cheating, the 2 points are indistinguishable because nobody knows which one I draw first, right? Somebody remembers? No. So we don't know which one is which. So basically, I can draw, for example, symmetry element is a mirror, like that. Yeah, there will be mirror symmetry because both are same. I can have mirror symmetries like that, any kind of mirror, and etc. So this group has also a symbol which is like infinity, which goes for infinite rotations around this axis, and then divided by m, which is the mirror plane, which is perpendicular to the principal axis. And there is one more m, which stands for the m's which are perpendicular. So which are containing the principal axis. So this is the Curie group or limiting group describing these objects. These are point groups, and all the crystallographic point groups are subgroups of something like that. If you consider the time reversal, then we actually should consider that during these few seconds at least, and maybe during this lecture, the point was remaining on the same place. So actually we should multiply by, let's say, group which contains identity and inversion and time reversal. And here as well. So I will write it in this way so that everybody understands. That is a combination of any element from here and animation of here. And those of you who are doing something with symmetry, then you can think about this SO3 group, that this one equals SO3, which is group of all proper rotations. These are these that engineers can do, so they can an object and they rotate it, right? If I keep the point, I don't know translation. Then it's extended times 1 and special inversion. This engineers cannot do. We can do it in cinema. We can put a mirror plane. We can look. We can make an image using the photograph. We can see the mirror image, but we cannot do really. You cannot have my left hand and make a mirror image. And also, engineers can do something in time. You know, you go to the cinema and you put the film on the. You reverse the time. Is it true? Is it? Everybody agrees? Okay, there will be one objection later about this time reversal operation, just mentioned during this previous talks. I'll come back to it later, and if not, Mael will remind me in the end. Okay, so this was my introduction to point groups. So point groups are subgroups of these things. And breaking I explained. So far, everybody is fine? Question? Mael was saying that polarization and magnetization transforms differently. You can, and there was some picture like that showing some action of symmetry operations. You can read this table also in different way. It's the same thing, right? Polarization and magnetization, if you put it in the space, it breaks different symmetry operations. Okay, so this is what I have in mind by breaking. And I like to also, instead of putting these minus ones and ones, sometimes draw the things geometrically. So instead of, so here from the picture, you immediately see that, for example, mirror plane perpendicular, it works. Mirror plane perpendicular to the magnetization. From the image, you see it keeps the magnetization untouched, while for the polarization, it reverses the origin, the arrow of the polarization. So that's one thing, to draw the arrow in this way. Another thing which is shown here, it's my nomenclature, I hope you will like it, that there is action of time reversal is also shown in the picture. Okay? So you will agree with me during this talk that whenever it's dashed, it means that time reversal is switching the direction. If it's a full line, so arrow with full line, then time reversal even quantity. It would be better to actually to make the dotted, the small arrow which goes around, but it's somehow difficult to draw it. So imagine that all the symbol is dotted. Okay. Once upon a time, it's now more than 10 years, I was wondering how many such type of objects exist. Especially I noticed that both these things are vectors, so they define some axis in space, right, like here, some magnitude, and they have also some binary sense or error or something like that. And so the question which I was worrying is how many sorts of arrows can be distinguished by space-time symmetry? You can define it a little bit better. How many sorts of indicators of oriented spatial directions can be distinguished by space-time symmetry? Or maybe, how many categories of quantities in physics are defined, which were defined so only by axis, magnitude, and a binary sign, which has some geometric origin, can be distinguished by spatio-temporal symmetry operations? And which of you knows the answer? Well, thanks. There are 8 of them. They are here. I'd like to draw your attention that each of these arrows can be reversed. Yeah? So on the top, we have one sense of the arrow. On the bottom, we have the reversed arrow. Okay? Also, if you are very careful, you see that in those which are on the right-hand side, there are 2 arrows each time, and the 4 on the left-hand side have just 1 arrow. This is quite important, and this is just the picture to memorize this. Also, I'd like to say once more that these which are dashed, it's supposed that the time reversal is changing their arrow, while the other on the left side, they are time even. They are not flipped when the time is flipped. And, okay. The reason, maybe you're curious why there are 8 of them, and if you'd like to understand the simple argument, which is absolutely robust, then you would need to look what is the one-dimensional irreducible representations of this group. This you remember from the talk of Mael, what are one-dimensional irreducible representations. Some matrices which are only 1 by 1, yes, have to transform together in the same way as the symmetry operations. And it turns out that there are just 8 of them. Okay? So what is shown here in this table is it's the table of irreps. So each line is one of these irreps. You have characters, which are directly the representation as well, because they are one-dimensional, so very small matrices. And you have, in the columns, there are symmetry operations in families. Once you know this, you can do many nice things with them. By the way, each of this irreducible representation corresponds to a quantity or object or some perturbation of the space. If you place it in the empty space, it decreases the symmetry to some subgroup of that one on the top of one point. And they are listed here, and you can see that all of them are different. So it's really different objects. You can just classify it by the 3 generators of this just by inversion, time reversal, and parallel mirror. Okay? Is it nice? You like it? Okay. So, first 4 of them are vectors. They really behave as vector, but you know from algebra. The other 4 are not. These 4 vectors has names: electric toroidal moment, electric dipole moment, magnetic dipole moment, and magnetic toroidal moment. And I use the letters G, which reminds you of some duration, but you should think that this is something which is time even, so it's like something that has to do with the sense as you go around something circular, like, for example, if you imagine something like that, if there would be some sense of going around, this is the symmetry which corresponds to electrical toroidal moment. Quite often people call it chiral, but it actually is not chiral, because if you make the sense, let's say, this way, I can easily flip it and make the other way around, which with the true chiral thing, I should not be able to do that. If you limit the dimension from 3 to 2, then it's chiral. But so this is G. Should be distinguished for axial vector, which is magnetic moment, which is the same thing, but you flip the sign by time reversal, and so on. Okay? So this is about vectors, but of course I can use the same two inversions and classify the scalars. Do you know how many scalars we have? Shout, who knows the answer? Someone can guess? Infinite number of scalars, yes. So perfectly, that's correct answer. But I'm asking about number of sorts of scalars which we can distinguish by the time and special time symmetry in the same way as I did with the vectors. Yeah. So whether I can classify them by how they react to symmetry operations. By the way, I didn't comment it. That one is a combined time reversal and special inversion. Okay, the scalars, we have 4 of them. So one is the usual scalar, like maybe you can think about mass or charge, which doesn't change when you apply the inversion or time reversal. Then you have, so it's identity representation. Then you have pseudoscalar, which is something which can be reversed by inversion of the space. We have also time itself, which transforms a little bit like scalar, and we have also magnetic monopole. Yeah, so we have 3 of them. We have 4 of them that can be distinguished by this table. And then you can play with all these. You can somehow make a vector product of different quantities or multiplying by scalar, and you can find how to transform these objects, make them in nice tables. And it's very useful. At least I found it very useful when going through different formulas, which appears, for example, in free energy, because the energy, remember, is a scalar, which normally in a system which doesn't change with the time should be the usual scalar, so should be invariant with respect to everything. So then you can combine these things which are breaking the symmetry into a piece which has the full symmetry, and this can go in the energy as a term, and things like that. What was also fun that because they break different combination of symmetries, if you have 2 of them, for example, these different vectors which are parallel in the same system, each of them is breaking different combination of symmetry. Sometimes you break also a third one. Actually, there are 7 possible combinations of these out of these 8 ones which can go together. So whenever you have in parallel 2 vectors of different kinds, which you can find in here, there is always the third one which is also present because the symmetry allows only this. Either you have only one irreducible representation which is broken, or you have triplet, or you have all of them, which is also sometimes useful when thinking about phase transitions, magnetoelectric effects, electromagnons, etc. Okay? One more story. I draw here these 2 points, and it is long after we have done this work. I had another student, Casey Erb, and we wanted to make something in computer which verifies something about some tables, which I'll show you later. And we were thinking how to represent these 8 quantities in a computer. Remember, 4 of them are vectors, and 4 of them are not vectors. I call them bidirectors because they have these 2 arrows. we know that actually there are some special kind of degenerate tensors of second order. So for those who are worrying that something is wrong with the theory, everything can be also translated in the more complicated language with two indices. But these objects, when we wanted to put it in the computer, we didn't want to work with tensors, second order rank tensors. So we were thinking how to do it. And finally, we decided that we realized that they are related to dipoles. If dipole, you imagine something like having 2 points which are very close together in a limit, and they still keep some property. For example, they break the symmetry in some way. Then, of course, everybody knows the electric dipole. When one is positive charge, the other is negative charge. Then because one is positive, other is negative, they are distinguishable. So you know how to write the arrow. We, for example, agree that we will go from negative to positive, like we do in ferroelectrics. So then, this polarization corresponds to dipoles, so 2 points which are different. But they are different in a specific sense. If I would have 2 points which have the same charge, they would define this, maybe I like this picture most, okay? So they would define this neutral bidirector which has the same arrows on the both sides. Okay, I can have positive charges if you flip it by something. I don't know, don't think about how, but I can have a quantity which would have arrows inside that would have could be decided that we would call associated with negative charges. So you can represent the double charge. You can generalize the idea of dipoles to something with just 2 similar charges. Now, how to proceed, for example, with this one? So this one describes, let's say, something which was where you applied the torsion, and the torsion remained there. So I can imagine, for example, DNA or some screw. And of course, it could be one hand or the other way around. And this is a chiral object. So if you turned it in one way, whatever you do with it as an engineer, you never can get the other one. So could it be also a dipole? And if yes, so what should distinguish these points from the case of this one? Someone knows the answer? You actually need something which has a property which is scalar but chiral. And if you have both ends left, that would be chiral, left-handed. If you can represent something which is right-handed chiral, you would have on both hands the right hand. And finally, of course, you can have something like this, like this one, the electric toroidal moment, which, where you would have on both on one side the left-handed scalar, and on the other hand, on the other side the right-handed scalar. And you can so I can show you the picture. So you can have this neutral bidirector polarization with charges, and with enantiomorphic scalars, you can define the electric toroidal moment and electric chiral bidirector. And now if you use the other two charges, you can make exercise that you can get all 8 of them. So are these arrows somehow useful, or it's just some game? So one of the things is that the order parameter, so polarization and magnetization are known to be order parameters of ferroelectrics and ferromagnets. So what about these other arrows? So for example, the toroidal moment, which is this symbol, which is the magnetic time reversible, time odd polar vector. So it could be other parameter in this compound. Please believe me, I can we can discuss later if you would like to know more. This G electric toroidal moment in another compound, by the way, discovered by one of the speakers, which will be in the next, you will hear in the next week. So that's something about arrows, scalars, and description of point group symmetry, playing with symmetry operations. Now I would like to introduce the concept of species. So species are really late. So in this paper, which is often criticized, the Curie principle, the one which introduced Curie principle, there is something very important. One sentence which nobody, I think, is objecting, that it's the dissymmetry which makes the effect. And I think it's very, very important. It's often forgotten. So actually what is important is not so much only the symmetry itself, but the symmetry breaking. Because when you break the symmetry, it's only then you realize something. When the symmetry is very high, it's like if everything is very high temperature, or you don't see anything, just one point. Once you have some information, you break the symmetry, it's now when you can start to realize, there is a special direction, and maybe you can count the number of directions, yeah? But before, if there is nothing, just one point, it's very difficult to do anything. And therefore, what we would like to propose is very important to consider group, subgroup related to symmetry breaking. And these are called species. It's a concept which was introduced already in 70s by Ketsuro Aizu. I will mention later his reference somewhere. And I would like to show as an example what is meant by that. So this is a famous group of Mael Guennou, MM2, and you see it's subgroup of MMM. He explained that. So for example, the path from MMM to MM2 corresponds to the species. It's group, subgroup relationship. Important is that not only there are two groups which are somehow related, this one has less elements, which is written here, 4. This one has 8 elements, so 1/2 disappeared. But also important, we somehow in this have in mind idea that we understand that some elements of the high symmetry group corresponds to the ones of low symmetry group. And in all these cases, it's not very important to mark it because it's somehow obvious that one of these mirrors disappears and these two is staying for the ones which are there. But there will be some more complicated cases, and I will explain. Anyway, so here you can see that if you have triclinic with inversion, you can decrease the symmetry of triclinic without inversion. This is the species, triclinic ones. Then species, so this is all these are monoclinic groups, 2/m, m, and 2. And so the species which starts from the monoclinic and goes to something lower symmetry, we call monoclinic species. So that's why in these plots I put it in a bold rectangle. I will show you later why it is important. But the species is something which goes from higher group to the lower group, and there could be some intermediate. So for example, species is from 2/m to 1. So you lose all symmetry elements except for of the identity. This is a species. You go from 2/m to m. This is also a species. Yeah? So it's the summit, and it's the higher symmetry and lower symmetry, just two groups. Okay, but it's convenient to put it in these plots where you see like many paths. But in principle, the species is just 2. So if there are different ways how to go, it doesn't matter for the definition of the species, okay? I'll skip that one. No, I think I have it. So what is important, that species is a group, subgroup, and somehow there is a relationship between orientation of the symmetry elements in the low symmetry group with respect to high symmetry group. So we call it oriented. And G bigger than F means that F is a subgroup of G, and this oriented means that sometimes I have to indicate how it is oriented. So for example, you can go from the group 4 to 2 to group which has only twofold symmetry axis. Then I have to distinguish whether it's along the principal symmetry element, which is the fourfold axis, or perpendicular. So I use these little subscripts, which are nevertheless more or less intuitive what they mean. And this is, let's say, the main thing which I think is useful for crystallography. And now the part of the thing which I will be showing, it was you can find it in that paper. And it was my colleagues Petr Ondrejkovič and Jana Přívracka and Vašek Janovec who contributed, each one considerably in a different way. It was a big teamwork. So again, on the same idea, if you think about high symmetry cubic symmetry, then you have different mirror planes. Some of them are pink, they are perpendicular to the fourfold axis. Some of them are gray, they are like bisectrix at 45 degrees, and we have to distinguish them. And for that we use this cross when they are perpendicular, or this backslash when they are oblique to the tetragonal axis, or the principal x, y, z directions. So with that, then we can distinguish, for example, group-subgroup relationship between this high symmetry group. We can have species which goes to which goes to MMM, but where one of the M has a slash, or to the MMM, one of the M has a cross. So these are different species because they lead to different physical situations. Because you kept different mirror planes, they are oriented differently with respect to the other elements. This has to be distinguished. But if you agree with this sort of game, I don't know if it works, if I can go like that. Maybe yes. It's a top. I have taken the berry face now. Okay, so with that, you can understand what are the species, and especially because my colleague Petr Ondrejkovič make a very nice tool which allows you to do it interactively. Anyway, but I'll go through. I'll show you later because I don't like to break the PowerPoint presentation. There is one more thing, is that number of these combinations is finite, and it's only 212 possible group subgroup reductions types in the space covered by these 32 point groups. And they can be all listed. So you have this table which actually Marty Greg was introducing, so I don't need to explain that. So what we have been showing here in addition, that you can see number of domain states, as Marty said, and then we have also put these symbols which are saying whether we can distinguish the domains by quantities which transforms as all these different kind of vectors or bidirectors. Now I should explain maybe two things. When there is this spontaneous symmetry breaking, so symmetry is lowering, there is always domains. So you never see here that there is always bigger than one. Yeah? So when you break the symmetry, you somehow have to restore it, and so it's intimately related with domains. But one has to understand, because we are classifying the things according to macroscopic symmetry, so point group symmetry, then these domains which are enumerated here, they are macroscopic domains. not in the sense that they are big, but in the sense that we are counting those which can be distinguished by something which is a macroscopic property. So something which needs to be probed by macroscopic average probe, and not something which depends on exact position of atoms. So it would be antiferroelectric. You can have antiphase boundaries where you shift the lattice by half a unit cell, and you get something different. So between these antiphase boundaries, so you have two domains. These are real domains, but you will never see it in optical microscope. You need to see individual atoms. Huh? So this gives you a number of the macroscopically distinguishable domains, and this is why we use these terms of macroscopic symmetry breaking also. And if you have polarization, polar vector, then, and you see you can distinguish them, these are ferroelectric phase transitions. So now this is something which I would like also to insist. There are many definitions of what is ferroelectric material, but basically it tells you that you have to be able to switch it. To be able to switch it, hysteresis is somehow related to the same story. So if you can switch it, you sometimes don't switch it completely, or you wait some time, so it's everything included. But to switch it basically in old times means that there are domains. Now we can switch everything because we are so powerful. But in old time, it means there was a domain wall which you can pass through. And if this domain walls differ by some component of something which transforms as polarization, then it's ferroelectric. It's very easy definition which allows you to know just by symmetry, is the material potentially ferroelectric? You just need the point group of the high symmetry and low symmetry, because ferroelectricity in principle is defined as a macroscopic phenomenon. It's special average polarization. Okay? That's why it's possible. So you can see immediately how many of these possible 212 species are ferroelectric and which are not ferroelectric. What I found very interesting, which we didn't understand in 2016 when we first published the paper with Vašek Janovec, that actually the neutral bidirector tells us whether it's a ferroelastic material. So in all these times, people were, already in this, you have seen it in some talks, that draw it here, that if you would like to represent polarization or ferroelectrics, you make an arrow, okay? So you use different color for magnetization. I like to do something like this. Okay, that's for magnetization. So you have ferroelectrics, ferromagnetics. And then if you would like to have ferroelastics, then people draw this thing. Okay? But actually, if the two domains can be distinguished by neutral bidirector, then it's the same thing. So actually this equals that one. Okay? And you can have ferrotoroidal phase transitions, or ferroaxial, where the other parameter is the chiral bidirector, etc. You can see. And these symbols, sometimes they are half empty. It means some domains can be distinguished, but not all. And this was discussed with Marty, so I can go through this very quickly. If you wish, I can go back. So we have 212 species of macroscopic symmetry breaking. I was playing with groups which are not depending on time reversal. If you do it with time reversal point groups, magnetic point groups, then it's a little bit more of them, actually 1602, but I will not bother you with them. What is interesting now, let's think how many types of ferroics we have, okay? And I would like to, I think I don't like to change the current paradigm or definition or something like that, but when you read the literature, it's sometimes too good to know what is the history perspective. So multiferroics actually came from the ferroic term, which according to the paper by Hans Schmidt in 2001, this is quotation from that paper, was actually coined by Aizu, which was introducing the species. He was introducing also the magnetic species. And he said that he coined the collective term ferroics, ferroic for ferroelectrics, ferromagnetics, and ferroelastics, the ones which I've been drawing there, because they have common ferro, X, and domains. Of course, this is a joke, but it's in the abstract of the paper. But what is important, that can be switched. Domains that can be switched, okay? And the fact that they can be switched is somehow understood in the times, in the 70s, that they can be switched by stimuli of mechanical origin or electrical origin or magnetic origin. So that's why we have these three. We can make a combination. So you have also cases when you need to switch the material by applying magnetic field and electric field together, or also the strain, etc. But whenever you can switch, that would be called ferroic material. That was in 1970. Then in 2001, there was this Hans Schmidt paper who actually thought, okay, we have also this magnetic toroidal moment, which was this dashed arrow. So I will add it here. So he was saying that in addition, we should have this vector which has this symmetry property. So it was 2001. And then 2012, there was also found experimentally material which was ferroaxial. So it was also realized that this can be macroscopic order parameter. So all four vectors are there, and one bidirector. Now, actually, in later, which I don't know the references, but partly because of these people like Manuel Bibes, Nicolas Paldin, Jim Scott, Ramesh, BFO, and others. Also, the antiferromagnets became considered as multiferroic. So it became a little bit messy what you include. But anyway, if you include all these vectors and this bidirector, then it makes sense also to make all of these 8 bidirectors as possible order parameters. But in addition, in parallel with this point of view, thinking about some macroscopic vectorial or bidirectorial orderings in the crystal, there was this idea which was pushed forward by Bouzehouane in 1989. He was basically saying that ferroic phase transitions are defined as non-disruptive phase transitions involving change of point group symmetry. If you take this standpoint, so basically any point group symmetry lowering, one of these 212, is sort of ferroic phase transition. And this was actually adapted in 2013 in the International Tables of Crystallography as a definition. So if you think about that, then even if none of these 8 is frozen and allows to distinguish your domain states, we might still think to call this material ferroic if it belows the symmetry, because the order parameter could be higher order tensor. And there's always something which distinguishes it. And it could be even interesting, because then your information, or you cannot be read it by magnetism or anything. But anyway, so I put the picture of Vasek Janovec, which was, I think, one of these who pushed it to the international tables for crystallography. But since there is no publication, then I cannot really, at least I could not find the reference. So let's see, how do I do with time? So this was my main message. These isospecies, I think, should be used. They're useful, and I think they are relatively simple, the ideas behind. Now, why it is also important that if you know the species, so the combination group-subgroup, which is oriented, then directly you know this defines what are the spontaneous components of different vectors and tensors. So, and this was also tabulated. This is Vašek Janovec's long-term work. We just somehow, in this publication, we make some access to it to the community, which is available because you can just click on the species and you get these tables. And so what is there is for a given, for example, this is this ferroaxial phase transitions. So it's if you know the Nye book of properties of crystals, so I think I have somewhere the reference as well. So these are these Nye matrices which are a little bit reorganized, but what you have there is explained on the left-hand side in this Jan symbols, which I don't know whether you are familiar, but I think that it will be introduced by Paolo or Radaeli, so I don't like to talk about that too much. But basically here you can see that we put here pseudoscalar. For example, V stands for vector, so it's like a polarization or vector. This is, for example, for symmetric tensor, which is dielectric one. You have piezoelectric tensor, etc. And we also put here this axial vector. So you can see in these matrices which symmetry elements are forbidden, then there is this just dot or nothing, and which are allowed, then there is some sort of dot, and which are only allowed below the phase transition and allows to distinguish the domains. These are red. So you can see at the same time what is in the high symmetry phase allowed and what in the low symmetry allowed. So for example, here I can distinguish the domains by the components of axial vector, and these dashes, which continues the points, are telling me that these numbers are same. And all it is explained there. Yes?
So those red dots there, these are the tensor components that are acquired through the phase transition.
Yes. So for example, this stands for elastic tensor, and you see that C11, C22, and C33 are allowed, and then C44 is allowed, but for example, but these were not allowed in the high temperature phase, but below the phase transition, they are allowed. And what is good also that they are in the same reference frame. So it's already transferred this matrix. So this is the cubic reference. So both matrices are in the same cubic axis. So here is the case of the ferrotoroidal transition, where the other parameter is magnetic toroidal moment. It's a funny situation. You have different domain states, and you can have in one domain, in one direction, magnetization, toroidal moment, and the polarization is perpendicular. So if you look for the matrix, here it is it's extended also with magnetic moment. So here we distinguish the magnetic symmetry. So the point group symmetry has also these dashes, which Mael was introducing. And again, you see that there is a magnetic moment allowed in the low temperature phase, and it has the X and Y components same. So it means it looks in this direction. Diagonal one. Then you can see here this the electric field or polarization. So the first component is allowed, so polarization is like this. And we don't show here the toroidal moment in this table, but you can also put the table there as well. The reason is basically that we don't need to put, we wanted to make some reasonable size of these matrices, and we made some compromise. But in principle, all can be calculated or tabulated. You don't need, the point is, again, we don't need to know anything more about the structure, just the 2-point groups. Also, there is a nice thing, there is a piezomagnetic tensor, and there is a beautiful paper recently published by Paolo Radaelli about outer ferromagnetism, and one of the beautiful results, which he clearly showed, but I don't like to steal his story, is that all these outer ferromagnetic materials are those which have this non-zero piezomagnetic tensor. So also you can just look in the table and you know whether your system is. It's a macroscopic property. All what you need is 2 magnetic point groups. Okay, that's again Vasek Janovec. I think I'm slowly having 1 hour. So the species are online. So this you can copy this web link, or you can find it in our PRL paper from 2016. Maybe I can do it later with you. Oh, yeah. Okay. So actually, so Petr Ondrejkovic was fascinated by the subject, and so I asked him many complicated tasks to do, but the result is this very nice web page which still works. And what you can do, what you have there are 4 things: simple list, subgroup diagrams, domain states, and property tensors. So all this you can find. It's clickable. So if I like very much this one, you click on this clickable object, and you can select your high symmetry point group. So it has to be in this bold frame. Okay, this is important to remember. So, for example, your high symmetry point group will be 622, so it has to be in bold. You don't click on that one. Yeah, you have to click. Or you can find, for example, 42 here, but you don't, it's not in the bold one, okay? So if you would 4 you have to go 4 here, okay? So you click on it, then you obtain a new diagram which tells you what are all possible subgroups of that one, and also the oriented one. So you click second one, for example, we would like to go for 4 divided by into MM2. Now you see there are 2 MM2s. MM2 with slash, and MM2 with, MM2 with horizontal bar and with the vertical bar. If you know that your two-fold axis, which remains in the system, is parallel to original 4, then you click on that one. After you have that, you directly go to the species. So you have the species we better described with all the elements, not with the shorthand information. You have the matrix, which defines you some of the basic tensors in the high symmetry phase, and the low symmetry phase. By color, they are distinguished the new elements or new links which appears, and they are all explained there. Yeah. So I think it's very useful, and also there is some info in each which explains what it means, so you don't need to do much. You can also, there's this search tool where you can directly go to the number of species, 73, for example, 173. You submit the number, and you go to the other symmetry. So I just would like to advertise that, and I recommend you to play with that, and I think it can be useful. Okay, so I'll try to go back to my presentation if I manage. How much I'm doing with time? How much? Yeah, so, okay. So, one thing I would like to mention, I don't know if some speaker is going to talk about electromechanical compatibility of domains. Probably not. Then I think it's worth to little bit mention that, especially in ferroelectrics, in good ferroelectrics, we have large polarization and there are insulators. So there was already discussed that ferroelectrics like to avoid the depolarization field, so they have domain walls have to be compatible. In addition, more complicated little bit is this condition of the mechanical compatibility. So I would like to maybe give you an example on one material, which is gallium, molybdenum, selenium, or all this family of GVS materials, which we used to work with together with people in Dresden. And there is a phase transition, which is species number 172 in our list. I'd like to advocate to use these numbers because it will facilitate others to using the table. Yeah, because even for you, I think 10 years ago, if you'd like to do something, it's always very quick. If you just know the number, you easily find the species. So this is minus 4 3m to 3m. You see how are you can easily find the matrices. And yeah, so what you can find here, that different domains can be distinguished by the red elements. Here you can see that there is polarization, so it's a ferroelectric phase transition. It's a ferroelectric material because it's domains which can be distinguished by polarization, therefore it can be switched. But also there is strain. It's a little bit similar like in the case of that Marty Gregg was talking about in boracite. So the strain is associated with the polarization. And if you would like to know what are the orientation of domain walls, which are mechanically and electrically compatible, it's basically all you need to know is this part of this matrix. From that you can get all. I will not do it in detail here, but basically you need these two things. And I'll skip it. Maybe I can show it pictorially, that in this material we have 4 domain states. And so elastic tensor can look in this ways, depending on which polarization it is. So it's, again, polarization can show in 4 different directions, which are shown here by the yellow, green, blue, and red. So it's also the case when polarization cannot be switched by 180 degrees. The symmetry says that if you switch by 180 degrees, it's not the same thing. It's not the same energy. So you have only 4, you don't have 8, even though it's rhombohedral. And each one has a different strain, and one strain corresponds to one polarization. So it's 1, 1 to 1. It's full ferroelastic, full ferroelectric. Now, if you would like, if you in part of your crystal, you have this sort of strain, and around you would have different strain. The question is, what sort of domain boundaries are possible in between? So this can be done in this way, that you use this mechanical compatibility condition, which basically tells you that you should solve the equation when you take this tensor and make a difference, and you are searching for the plane which satisfies this equation. So graphically, it's that you just make the two the strain tensor between the two domains, and if you make the difference, so here again, I didn't stress, but it's a nomenclature of Nye, so some of you would know if there is a connection between two positions in the matrix, it means it's the same value in absolute value, but opposite sign. So because you are make a difference between something which is here opposite sign, so it remains there. If it's same, it vanishes. So this is the difference graphically, whatever are the numbers in the matrix. And then if you think about solution of this equation, if you rewrite it, there is some number and because it's symmetric maxing is the same number, so the number doesn't matter. I can divide it by the number. I can divide it by the full dot, if you wish, and I get just this sort of equation of motion. It just tells you that one mirror which is mechanically compatible is perpendicular to x1, and the other is just given by this normal vector. So I know immediately what are the orientation of domain walls. I don't expect you follow me in details, but I would like to just indicate you how you can obtain this. Then you can make a sort of matrix in which you have polarization of one domain state and another domain state, and you can see, you can just put the results for other orientations of the charge domain walls or neutral domain walls. What I would like to tell you that all this can be done just by knowing the group, subgroup has to be oriented one, so one of the species. You know the number of the species, you know what sort of domain walls which are mechanically compatible are there. These things are tabulated, but it's good to know, to understand where it comes from, and that you don't need to know much more. So we use it to interpret some data. I will skip that. I will not talk about these things. I would like to just convey the message that there are 8 types of quantities which we often represent as vectors, even though 4 of them are not vectors. But you can find many in physics. We are using the algebra. Vectors are so nice. Just you put 3 numbers, dash before and dash in between and brackets around, and we can do calculates. We can put it in the computer. So as far as we don't play with the symmetries and time reversal and things like that, it's fine. But otherwise, sometimes it makes some strange things. But quite often, it's enough to remember. So people are dealing with that by remembering, or they use tensors and things like that, or different ways. But it's good to know there are actually 8 of them. So example of where the label doesn't correspond to the symmetry of the object is the Burgers vector of the screw dislocation. The screw is the symmetry of bidirector. The vector, Burgers vector, is a vector. So think of it when playing. Now, if you like that, you can think, okay, we can have these vectors are bidirectional, these arrows. We have 8 types of arrows. We can make topological defects. We can make a wall. We can make a Bloch wall, Mael wall. Thinks about what's the symmetry of that object, how it will react, and what it transforms. Does it transform momentum? Does it transform? Is it chiral, etc.? We can, of course, make skyrmions out of them. So we can have polar skyrmions. We can have magnetic skyrmions. I mean, what does it mean? Now I'm giving this interpretation to the word. Magnetic skyrmion, the skyrmion, it's topological texture in magnetization field. Now I can have skyrmionic texture in toroidal moment field. Yeah? So you can have all these, and you can think about the symmetry. One thing which I like is if you think, for example, about topological number of the Bloch skyrmions. We call it topological number, but topological number of Bloch skyrmion, it transforms as a vector or as a bidirector if it would be bidirectional one. Actually, it's nice. The Bloch skyrmion of magnetization has a symmetry of magnetization. Topological symmetry of electric polarization. Skyrmion in the skyrmion topological defect in ferroelectric field has symmetry of polarization, which is parallel to the center of the skyrmion, etc. One for Michel. So there was I'm thinking about continuous world. So also the Jeloshinsky-Moria interaction has its counterpart in continuum models. Actually, Jeloshinsky was introducing them, if I remember well, in this way. So there are terms in the Landau-Ginzburg expansion for certain magnets, which are linear in the gradient and quadratic in magnetization. They are only allowed in certain symmetries, and in different symmetries they have different form. And these terms, if you look of them, because they are quadratic magnetization, they are also, if you replace magnetization by polarization, they're also allowed. So the same sort of analogical continuous Jeloshinsky-Moria interactions, which are inducing the skyrmions in phenomenological theories, they're also possible in ferroelectrics. Of course, the question is how big they are, etc. But the conditions for symmetry are the same. Actually, what is interesting that some of these, in uniaxial magnets, the symmetry of these terms is just given by these vectors or bidirectors. For example, the one which gives the Bloch skyrmion has the symmetry of chiral bidirector, which is oriented along the z-axis. And the one which goes Snell skyrmions is the symmetry of polarization. That's why if you have ferroelectric ferromagnet with this sort of Jeloshinsky-Moria interaction oriented along the polar direction, you can have Snell skyrmions, etc. Okay, so just I would stay with here. I'd like you to think about, and I hope you enjoyed a little bit this lecture.